Today, we're diving into a material that's so incredibly thin, it's basically two-dimensional. But hidden inside its atomic layers is a secret that could completely change how we build everything from our computer chips to powerful new microscopes.
So just think about this for a second. What if you could change how a material bends light? Not by changing what it's made of, but just by making it a few atoms thicker or thinner. I know, it sounds like something straight out of science fiction, but it's actually the key to a brand new discovery. And this is the number that got scientists' attention. We're talking about a nearly 25% change in how well a material can bend light, its refractive index, just by shaving off a few layers. Now, nobody saw this coming, and it kicked off a really fascinating scientific detective story.
At the very heart of this mystery is a 2D crystal called copper indium thiophosphate. Yeah, that's a mouthful. So for today, let's just call it CIPS. And as you're about to see, CIPS is, well, it's very, very special.
Okay, so why should we even care about bending light? Well, it's because the secret that CIPS is hiding has to do with its incredible ability to control a very specific and very valuable part of the light spectrum.
You know, being able to precisely control blue and ultraviolet light, that's kind of the holy grail for a ton of huge industries. We're talking about the super high precision lithography used to make the chips in, well, all of our devices. It means getting sharper images in high-res microscopes and building the next generation of super-fast optical communications. Basically, if you get better at this, you get better at everything.
So, to figure out what was really going on here, researchers at TU Delft and Radboud University set up this really clever experiment. They already had a hunch that CIPS was interesting, but I don't think they had any idea just how strange things were about to get as they started to methodically peel back its layers.
The whole process they came up with was pretty ingenious. They'd take a tiny flake of CIPS and put it into this cycle. First, they'd measure its optical properties. Then, they'd use this really gentle argon beam to shave off just a few nanometers. And then, they'd measure it again. Thin, measure, repeat. It's a really painstaking process, but it's how you build a complete picture of a material at every possible thickness.
And this right here, this is their aha moment, caught on a graph. See, everyone expected the material's properties to be pretty much stable, right? But look what happens. As the CIPS flake gets thinner, specifically between about 170 and 22 nanometers, its ability to bend light, that's the refractive index you see with the orange dots, it just goes haywire. It drops like a rock. This anomalous regime was the first big clue that something truly bizarre was happening inside this crystal.
But that weird anomaly? It wasn't just some strange quirk. No, it was actually a signpost, and it was pointing directly to a hidden superpower, one that would end up shattering existing records.
Now, to get what this superpower is, we need to quickly talk about a key term, birefringence. It sounds complicated, but it's basically when a material splits a single ray of light into two separate rays, and each one bends at a slightly different angle. The bigger that difference is between the angles, the more control you have over the light's properties, like its polarization.
And this is where CIPS just becomes a total champion. This chart is comparing the birefringence of CIPS to a whole bunch of other advanced materials. And, as you can clearly see, especially over there in that critical UV blue range on the left, it's not even a competition. That red line for CIPS just skyrockets past everything else. It's in a league of its own.
The absolute peak of that power is a bireferences value of 1.24. Now, to put that into perspective for you, that is the highest value ever reported for any material in this part of the light spectrum. It is, quite literally, a world record.
So here's the real kicker. As co-first author Houssam Mrabet Haje explains, you get this absolutely insane level of control over UV light right out of the box. You don't need all this complicated engineering or nanostructuring. The material just does it, all on its own. So, okay, we've got a strange anomaly, we've got a record-breaking superpower, but why? What is actually happening inside this crystal to make it act this way? Well, the answer seems to lie with some tiny, tiny dancers.
First thing you need to know is that CIPS is a ferroelectric material. Just think of it like it has a built-in electrical field, like a tiny magnet with a north and south pole, all created by how its atoms are arranged. And in CIPS, the key players creating this field are copper ions that aren't locked in place. They can actually move around a bit.
So here's the theory. When light enters the crystal, its electric field starts to interact with that internal field created by those mobile copper ions. Now imagine these ions are like dancers on a dance floor. What the researchers figured out is that the size of the dance floor, which is the thickness of the crystal, actually changes the dancer's formation. And that change in formation fundamentally alters how the material interacts with and bends the light that's coming in.
As the lead researcher puts it, this is really the heart of the discovery. The secret isn't just that CIPS has these mobile ions, it's that the behavior of those ions is directly tied to the physical size of the crystal. It's a completely new way of thinking about how to tune a material's properties.
So what does this all mean for the future? Well, this isn't just a story about one weird crystal. This discovery could open up a completely new frontier in materials science.
The principal investigator, Mazhar Ali, points out that this whole mechanism, where you have mobile ions and this built-in electric field working together to shape light, that could be a general principle. CIPS might just be the very first example of a whole new class of tunable optical materials.
And that brings us right back to the real-world impact. We're talking about tunable components for making chips, more powerful microscope lenses, faster communication systems. It even opens the door to creating on-chip devices where the flow of light is controlled not just by electrons, but by the physical movement of ions themselves. That's a huge deal. You know, for centuries, we've designed materials to be as stable and unchanging as possible. But this discovery just flips that entire idea on its head. It suggests that the future might lie in materials whose properties are meant to be dynamic and tunable and dependent on their environment. And it leaves us with this one big, fascinating question. What new technologies could we build if we start thinking of materials not as static objects, but as active participants in our technology?